Hello and welcome back at the Finetlink channel. You have to be conscious that no matter how effectively you set up your network, something will always stop working correctly or even stop working completely at all. This is a simple truth about your network. So even you already know quite a bit about routing, you still need to know how your router actually works. And this knowledge is very important if you want to be able to troubleshoot your network. And so that's what we will do in this video. So we will learn about routing concepts where the objective of this material will be explaining how routers use information in packet to make forwarding decisions. So we will explain how routers determine the best path. We will explain how routers forward packets to the destination. We will even configure basic settings on a router, and then we will describe the structure of a routing table, and lastly, we will compare static and dynamic routing concept. The material will be in two videos, and in the first one, we will see the first three topics. So before a router forwards packets anywhere, it has to determine the best path for the packets to take. Because Ethernet switches are used to connect end devices and other intermediate devices, such as Ethernet switches, to the same net. But a router connects multiple networks, which means that it has multiple interfaces, one for each belongs to a different IP network. And when a router receives an IP packet in one of his interfaces, it determines which interface he needs to use to forward the packets to the destination. And this process is known as a routing. The interface that the router used to forward the packets may be the final destination, or it may be a network connected to another router that is used to reach the destination network. Each network that a router connects to typically requires a separate interface, but this is not always the case. So, the primary function of a router is to determine the best path to forward packets to the destination based on the information that he has in his routing table, and the second function is to forward these packets to the right destination. And here we have a video that explains that how the packets from network 192.168.1/24 will go to the router, and the router will check his routing table and will find where is the destination network. So he first reads the router 2, and then the router 2 will check the packet, and the router 2 is connected with the final destination. Because the router 1, the final destination was a remote network for him. So he had to send the packets to the router 2, and the router 2 will send the packets to the right destination. Is the network that is connected directly to one of his interfaces. So the question is, what is meant by the router to determine the best path in the routing table? The best path in the routing table is also known as the longest path. The longest match is a process that the router uses to find a match between the destination IP address of the packet and the routing entry in the routing table. The routing table contains route entries consisting on a prefix and prefix length. For there to be a match between the destination IP address of a packet and a route in the routing table, a minimum number of far-left bits must match between the IP address of the packet and the route in the routing table. The prefix length of the route in the routing table is used to determine the minimum number of far-left bits that must match. Remember that an IP packet only contains the destination IP address and not the prefix length. The longest match in the routing table has the greatest number of far left matching bits in the destination IP address of the packet. The route with the greatest number of equivalent far left bits, or the longest match, is always preferred as the best route. Here we have a table of IPv4 addresses, and here we will find the longest match. An IPv4 packet has the destination IP address as 172.16.0.10, and it is converted in address in binary. And the router has 3 entries in its IPv4 routing table that match the IPv4 destination address of the packets. And here we have the route entry as 172.16.00/12/18 and /26. So we convert those 3 addresses in binary addresses. And all of the 3 routes has the longest match and would be chosen to forward the packet. But remember that one of these routes needs to be considered a match there, and so there must be at least the number of matching bits indicated by the subnet mask of the route. And as you can see from the subnet mask of the route, is the address number 3 the best longest match. And now, as we did with the IPv4 address, we will do even with the IPv6 address to find the longest match. Here we have a table that the IPv6 packet has a destination address as 2001 DB8 C00 and 99. Here, this example shows 3 route entries, but only 2 of them are valid match, with one of those being the longest match. The first 2 route entries have prefix length that have the required number of matching bits as indicated by the prefix length. The first route entry has a prefix length of /40, matches the 40 far left bits in the IPv6 address. The second route has a prefix length of /48, which means 48 bits matching the destination IPv6 address, and this is the longest match. The third route entry is not a match because /26 requires 64 matching bits. So only the first 48 bits match, so this route entry is not considered a match. So how a router builds his routing table? The routing table of a router consists of prefixes and prefix length. And the question is how a router learns about these networks. And in this case, how does a router 1 that we have in this figure populate its routing table? To populate his routing table, router 1 needs to identify directly connected networks to him, remote networks, and default routers. So what is a directly connected network? These directly connected networks are the networks that are configured on an active interface of the router. A directly connected network is added to the routing table when an interface is configured with an IP address and a subnet mask or a prefix length, and it is active, which means it's up. And then we have the remote networks. These networks are not directly connected to the routers. Routers learn about these remote networks in two ways. Instead, by using the static routes, they are added to the routing table when a route is manually configured by the administrator. And we have the routes that are learned by dynamic routing protocols. These are added to the routing table when routing protocols dynamically learn about the remote networks. Those dynamic routing protocols may include enhanced interior gateway routing protocol or open short path first, as well as several other protocols. And then we have even the default route, where a default route specifies a next hop router to use when the routing table does not contain a specific route and matches the destination IP address. Now that the router has determined the best path for a packet based on the longest match, it must determine how to encapsulate the packet and forward it out to the correct egress interface. Here in this figure, it demonstrates how a router first determines the best path and then he forwards the packet. And as you can see, when he gets the packet, he checks the packet in the routing table to identify if there is a match in the routing table for the destination IP address. So where he finds the longest match between destination IP address and the entries in the routing table. And after he finds one entry, he forwards packet directly to the destination device if the IP address is directly a connected network. And if it's a remote network, he forward the package to the next hop router. And if there is no match in the routing table, he drops the packets down. So let's see how he does decisions. So when he forwards the packet to a device on a network directly connected, if the route entry indicates that the egress interface is a directly connected network, this means that the destination IP address of the packet belongs to a device on the directly connected network, and therefore the packet can be forwarded directly to the destination device. The destination device is typically an end device on an Ethernet LAN, which means the packet must be encapsulated into Ethernet frame. To encapsulate the packet in the Ethernet frame, the router needs to determine the destination MAC address associated with the destination IP address of the packet. The process varies based on whether the packet is an IPv4 or IPv6 packet, because if it is an IPv4 packet, the router checks its ARP table for the destination IPv4 address on an associated Ethernet MAC address. If there is no match, the router sends an ARP request. The destination device will return an ARP reply with its MAC address. The router can now forward the IPv4 packet in an Ethernet frame with the proper destination MAC address. And if the IP packet is an IPv6, the router checks its neighbor cache for the destination IPv6 address and an associated Ethernet MAC address. If there is no match, the router sends an ICMP Internet Message Control Protocol versus 6 neighbor solicitation message. The destination device will return an MPv6 neighbor advertisement message with its MAC address. The router can now forward the IPv6 packet in an Ethernet frame with the proper destination MAC address. And how he got the decision to send the packet to the next hop router. This happens if the route entries indicate that the destination IP address is on a remote network. This means that the destination IP address of the packet belongs to a device or network that is not directly connected. Therefore, the packet must be forwarded to another router, specifically a next hop router. The next hop address is indicated in the route entry. If the forwarding router and the next hop router are on Ethernet network, a similar process, ARP and Internet Control Message Protocol version 6 neighbor discovery will occur for determining the destination MAC address of the packet as described previously. So the difference is that the router will search for the IP address of the next hop router and its ARP table or a neighbor cache instead of the destination IP address of the packet. And if there is no matching, it drops down. So let's see how he drops the packet. If there is no match between the destination IP address and a prefix in the routing table, and there is no default route, the packet will be dropped. So the primary responsibility of the packet forwarding function is to encapsulate packets in the appropriate data link frame type for the outgoing interface. For example, the data link frame format for a serial link could be a point-to-point protocol, high-level data link protocol, or some other layer 2 protocol. Here we will have example and we will see animation how the PC1 will send a packet to the PC2. You will see that the context and the format of the data link frame change at each hop. So at the first one, the PC needs to send the packet to the PC2. Here, since the PC2 is in a different network, PC1 will forward the packet to its default gateway. The PC1 will look in its ARP cache for the MAC address of the default gateway and add the indicated frame information. Remember that if an ARP entry does not exist in the ARP table for the default gateway, PC1 sends an ARP request, and then the router 1 would then return an ARP replay with its MAC address. And now that the packet reached the router 1, is the router 1 that needs to forward the packet to the router 2. He forward the packet to the PC2, but because the exit interface is on the Ethernet network, router 1 must resolve the next hop IPv4 address with the destination MAC address using its ARP table. If an ARP entry does not exist in the ARP table for the next hop interface of 192.168.2.2, router 1 will send an ARP request where the router 2 would then return an ARP reply. And as you can see, every time that the packets travel, the destination and IP address and the source IP address will not change. The only thing that changes is the data link layer frame. So the MAC addresses. Now the packet has reached router 2. And now that it has reached router 2, let's see how this packet will go to the router 3. Because router 2 now forward the packets. And because the exit interface is on the Ethernet network, router 2 does not have to resolve the next hop IPv4 address with a destination MAC address. When the interface is a point-to-point serial connection, the router encapsulates the IPv4 packet into the proper data link frame format used by the exit interface. Because there are no MAC address or on-serial interface, router 2 sets the data link destination address to an equivalent of broadcast. And now that the packet reached router 3, let's see that how the router 3 forwards the packet to the destination, which is PC2. Here, because the destination IPv4 address is on a directly connected Ethernet network, router 3 must resolve the destination IPv4 address of the packet with its associated MAC addresses. If the entry is not in an ARP table, router 3 sends the ARP request out of its fast Ethernet 00 interface, and PC2 would then return an ARP reply with its MAC address. And after he gets the information about the MAC address, what we'll do, we'll send the packet to the destination, which means that he will encapsulate the packet with the new destination MAC address and source MAC address. And as you can see, when the packet traveled through the network, the source and destination IP address do not change. The only thing that is changed is the data link frame when it travels through the network. And as we mentioned previously, the primary responsibility of the packet forwarding function is to encapsulate packets in the appropriate data link frame type for the outgoing interface. The more efficiently a router can perform this task, the faster packet can be forwarded by the router. Routers support 3 mechanisms about the packet forwarding, and those mechanisms are listed here in this slide. The first mechanism is a process switching. It's an older packet forwarding mechanism still available for some Cisco routers. When a packet arrives on an interface, it is forwarded to the control plane where the CPU matches the destination addresses with an entry in its routing table, and then determines the exit interface and forwards the packet. It is important to understand that the router does this for every packet, even if the destination is the same for a stream of packets. This process switching mechanism is very slow and is rarely implemented in modern networks. The other mechanism is fast switching. It's an older packet forwarding mechanism which was the successor to process switching. Fast switching uses a fast switching cache to store next hop information. When a packet arrives on an interface, it is forwarded to the control plane where the CPU searches for a match in the fast switching cache. And if it is not there, it is process switched and forwarded to an exit interface. The flow information for the packet is also stored in the fast switching cache. If another packet going to the same destination arrives on an interface, the next hop information in the cache is reused without CPU intervention. With fast switching, you can see that only the first packet of a flow is process switched and added to the fast switching cache. The next 4 packets are quickly processed based on the information in the fast switching cache. And the last mechanism is Cisco Express Forward, CEF, and is the most recent and default Cisco iOS packet forwarding mechanism. Like fast switching, Cisco Express Forwarding builds a forwarding information base, FIP, and an adjacency table. Wherever the table entries are not packet triggered like fast switching but change triggered, such as when something changed in the network topology. Therefore, when a network has converged, the forwarding information base and adjacency table contains all the information that the router would have to consider when forwarding a packet. Cisco Express Forwarding is the fastest forwarding mechanism and the default on a Cisco router and multi-layer switches. It builds the forward information base and adjacency table after the network has converged. All 5 packets are quickly processed in the data plane. And now we will go and see some basic router configuration after we are done even with packet forwarding and the routers. And since a router creates a routing table to help it determine where to forward the packet. But before diving into the details of the IP routing table, here we will make reviews about basic router configuration and verification tasks. So we have this network which will be used for configuration and verification examples. It will also be used in the next topic to discuss for the IP routing table. And here in this slide, we have an example for the full configuration of the router in the router 1 and the topology. So we configure the host name, we configure the password, we configure the password even for line console and virtual terminal. And then we configure the security of and we encrypted the passwords and we configured even a banner. And after that, we will go and configure the interfaces with the IP addresses for each interface, where we'll add even a description, and for the we will configure for both network IPv4 and the IPv6, and in each interface we will activate the interface with now shutdown. So we will configure the interface 00 that connects LAN 1, 001 connects LAN 2, interface serial 011 is linked to the router 2. And all those IP addresses that we configure in this interfaces, they are default gateways for the network that they are directly connected. And since we configure those interfaces with IP address, as soon as we add the IP address, they will be added as directly connected route to the router, directly connected network to the router. And as always, after we do configure the devices, what it is. So after we configure a network, some other commands that are very important are the command that we use to do the verification in our network. And those commands will include as a show IP interface brief, that it shows us information about the IP addresses for each interface and if they are up. And this is for IPv4. This is for the IPv6 network. And we have the show running configuration interface that it will give us description about more detailed about the interface. We have even command show interfaces. When we use show interfaces, it is followed by a certain interface that we want to check. In this case is for Giga Ethernet 00, and it's the information about this interface, if it's up and it's operating successfully, and if there had any packets that were dropped down and have any collisions. And we have even the show IP interface. With the show IP interface, it gives more details about the IP in a particular interface, like in this case for Giga Ethernet 00, and that is for Internet IPv4 network, and this is for the IPv6. It is important even the show IP route command, and with this show IP route we are able to identify the routing table for the router, and if the networks are connected directly or remote with in our router. And this command here is for the IPv4, and this is for the IPv6 network. And then it is important even the ping command to test the network connectivity. But as always, we sometimes need to filter what we are looking about in some commands. So we use the filter command output, and it's a feature that improves user experience in the command line interface, where it can be used to display specific section of output. To enable the filtering command, we enter a pipe character after the show command, and then enter a filtering parameter and a filtering expression. The filtering parameter that be configured after the pipe must be section. In this case, we are using section line VTY. So we are getting information only about the line terminal line, virtual terminal line, with include all output lines that match the filtering expression, as here. So we are looking all the IPv6 interfaces that are up. With the exclude, we exclude all output lines that match the filtering expression, like here that we are showing IP interfaces brief excluded as unassigned. So we are including only those IP interfaces that are configured. So interfaces with an IP address, and they are functioning up. And with the begin, we display all the output lines from a certain point, starting with a line that matches the filtering expression. Here, for example, we are showing IP route that begin with a gateway. So here in this example, we demonstrate some of filtering parameters. And in the next material, we will discuss about IP routing table and the static and dynamic routing and the differences between those two routing. Until the next session, hope you like the video at this channel, and if you do, share it with your friends, and do not forget to subscribe at this channel if you are new. See you soon.